I'm going to say if this was a 2, now I need it to be a 4. If this was a 3, now I need it to be a 6. And if this was a half, I need it to be a 1 now. Is everyone seeing that? Let me do it the halfway.
Maybe it'll, yeah.
Okay. So if I make that a half, everything's technically balanced, right? I have half of 2 is 1, and this side has 1 oxygen. Is there really any way to get half of an element? No. How can I simplify that fraction?
Now I get what you're saying.
The
Okay.
2 is going to cancel your half there. What you're really saying is, if I can make all the rest of them react, what really happens is it really does just use 1 atom of oxygen. But it must react in 2 to 2 proportions. It must take 2 of those ethyls, and they exactly produce 1 oxygen. So I must start off with 2 of these, and if I needed 2 of these, that's 2 carbons and 2 carbons, so I need really 4 carbons, right?
Mm-hmm.
And then it's, right? So I need a 6 here, and then that 1/2 gets canceled by our 2 there, and just becomes a 1.
So is that like the only time you've really ever put 1 as a prefix?
Yes, and you want to put 1 to remind yourself that you'd multiplied 3 by 2. Otherwise, you would normally leave it. But you're putting that 1 there specifically to remind yourself, I canceled a half. Without that there, something's not right just yet.
Will you do 1 in the opposite form, like where he gives you the product?
I don't know if he has one on here, but I will.
I don't think he does, but I have my study pack if you want to.
Is there one on there where he breaks it down?
So. Here's some decombs. Here's those. Here's the next page.
Okay, yeah. So if you're looking at your exam study pack, the heading says types of chemical reactions, and it says combustion, combination, and decomposition. I'm going to do that last decomp there, okay? I'm going to do that up here on the board. Let me write it up here. So he tells you, he says, write the balanced chemical equation for the decomposition, just ignore that this is here, of nickel 4-carbonate. So the charge on that nickel's 4. Charge on each carbonate is -2, so you need 2 of them. And he's told you that it's decomposing to form nickel 4 oxide and carbon dioxide. Okay. The tricky part on these is he's probably going to give you the name, and you have to get to the formula. Okay, that's half the work on this, right? Doing the charges for that like we did there. Everything else from here on here is just balancing it. He's already given you the product, so you don't have to react them down to elemental form. You just need to balance. Okay, 2 carbons on the left. Does everybody see that? I need 2 carbons on the right. So I need a 2 in front of the CO2. So that takes care of my carbons. I already have just 1 nickel. Did that fix my oxygens? Well, I've got 3 times 2, so I've got 6 over here. I've got 2 and 4, so 6 over here, so that fixed everything. So 2 decomps. One where he can give you the product, exactly what it makes. So it makes exactly this and exactly that. You got to be very careful when you do that, because if he's giving you exactly that, you have to get exactly that, otherwise it won't balance out. You'll drive yourself crazy. If he doesn't say, if he just says, do the decomp of this, and he doesn't give you products, take it down to elemental form. The tricky thing on that is your 7 diatomics. So, I don't know if I've showed you all this real quick trick rule thing. Your 7 diatomics start with element 7, and you count, and they make the shape of a 7. So start with element nitrogen. Element 7 starts your 7 diatomics. You go nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. But if you count those, 1, 2, 3, 4, 5, 6, well, there's 7 diatomic gases. Who's the only person? You need 1 more. element 1 hydrogen. Okay, that's your 7. Your 7 diatomics make a 7, and then you're missing one guy, and that's hydrogen. Okay, so be careful on this when you're taking them down to elemental forms. Be careful on your diatomics. It's another thing you'll drive yourself crazy on.
I actually found another one of those nanionics that I don't understand.
Okay.
And we just did, like, why does that's aqueous? Why does that stay together?
Because nothing falls out. Is it okay if I borrow this and do it? So I think this was just from a net ionic practice packet, but I'm going to do it up here for you. Again, just ignore this. Actually, I need a little more room. Put it over there. So you're given phosphoric acid, sodium hydroxide. So what kind of reaction is that? Well, I'm writing the rest of it.
Neutralization.
A neutralization. Mm-hmm. Okay, so because you're starting off with an acid and a base, they're both going to start off aqueous. So let's start off breaking everything apart. Okay, let's break everything apart for this. So what I'm going to break apart is the hydrogens. Okay, they break into +1 charges, and I've got 3 of them. 3 hydrogens plus 1. Then I've got 1 phosphate -3, also aqueous. 3 sodiums +1 each, aqueous, and 3 hydroxides, aqueous. Okay? Gonna keep breaking stuff apart. So I'm gonna break apart this aqueous here. So 3 sodiums +1, aqueous, and 1 phosphate -3, aqueous.
That'd be the total net.
Yes, because does that water break apart? Why? It's not aqueous. You don't break apart your liquids, your solids, and your gases. Okay? There was nothing around them to break them up. Something's happened here, and we want to key in on what's happened. That's why we don't break that apart. So you knock out your spectators. So people that appear exactly the same on the left and right, that's number of and charge. So I have 1 phosphate at -3, 1 phosphate at -3, 3 sodiums at +1, and 3 sodiums at +1. So what we really want to key on is happening here, the net part of what's happening is 3 hydrogens at +1 each are coming together with 3 hydroxides at -1 each, and what you're getting is 3 water molecules. Did anything happen to the phosphate besides it just changed the metal it was with, or it changed its cation? Did anything happen with the sodium besides it just gave up its hydroxide? No. This was a neutralization reaction. I think you're the one who said it. This is a neutralization reaction because that hydrogen and hydroxides eliminating each other. So that when you get down to what is actually happening there, this should be all you have. Okay? So your net ionics is literally just what's happening there. Don't break apart your solids. Don't break apart your liquids. Don't break apart your gases because that's something that's happening.
Then why is the answer this? Why is that the answer?
Is that for a net ionic?
Yes. Why is this the answer?
It's wrong.
I was gonna say, like, it doesn't make sense because this one does the same thing and this one.
That's wrong. This is supposed to be the same thing there.
That's
Yeah.
what I
He just didn't do that extra line of work. In your neutralizations, when you get down to here, you should only have aqueouses left for things that are locked up in either a solid, a liquid, or a gas. Okay, you should have eliminated all the guys that can run free.
What is this called?
net ionics, net ionic equations. About another 10, 15 minutes. Other questions?
Will you do like
Let's
some
do
of
it.
the
Let's,
molarity equation?
let me do a combustion really quick, and I'll do that. No one's asked about a combustion. I want to do a combustion so you can see that. I think we've done just about all the others in one way or another, but let's do a combustion because I know you're going to have it on there, and no one's asked about it yet. So let's do this one right off of the exam practice. So C3H8. Because it's combustion, what's your other reactant? Diatomic oxygen. One-way arrow. Only two products are CO2 and water. You have to provide that. Okay. Now we need to balance. 3 carbons. I need 3 carbons. 8 hydrogens. I need 8 hydrogens. And then your oxygens are the ones that will normally work themselves out, but we want to see what's going on with them now because we fix everybody else. So 6 oxygens here, 4 more there. So we've got 10 on this side, but only 2 over here. So what do we need in front of that O2? A 5. And we're balanced. The key for all these reactions is to do the right reaction. If it happens, you'll have 2 that won't happen. So there's a case in which a single displacement won't happen if the metal's not higher, more active than the metal it's trying to kick out. And a double displacement won't happen if you don't form a solid. One of your products has to be a solid. If they both come out aqueous, doesn't happen. You just dumped a bunch of stuff and a bunch of other stuff, and now it's all mixed together, but there's nothing really happening. And they have to all be balanced. Don't assume they're balanced. Loves to put like one number in there, and you automatically look at it and go, there's a coefficient. It's all balanced. Check it. Especially these top ones, like this right here. Just because there's numbers there, spend the extra 3-5 minutes and check them. Okay? But you still want to check. You still want to check. Even if it doesn't say, the equation is not valid unless it's balanced. Okay, and especially if you're using it for a problem, like to do a molarity or something like that, you'll work all the way through the problem, and then you'll see it, you'll go, it's not balanced. And you've got to go back and change all your coefficients and change all your numbers. Okay, so let me do a molarity real quick. We did a molecules a little bit earlier. Let's do this number 6 right here. So we're starting off with 10 grams of lithium hydroxide, and we're told it's completely reacted by 35.71 milliliters of phosphoric acid. And we don't know the concentration for that phosphoric acid. Don't assume this is balanced. Water has to be broken apart into hydrogens and hydroxides to balance, because that's what made it. Okay, that's what originally made it. So then you balance with hydrogens and hydroxides. Don't try to balance elemental hydrogen and elemental oxygen. It won't work. Okay? You're going to come out, and this guy right here is going to throw you off every single time. So balance, when you have polyatomics there, you balance by the polyatomics. So 1 phosphate, 1 phosphate. 3 hydroxides, 3 hydroxides. Okay? So that is balanced. So then we're asked to find the molarity here of the phosphoric acid solution. So we were given the grams of the lithium hydroxide. We want to get that to moles, because I can use the molarity for that lithium hydroxide and jump to the molarity of what I need for my phosphoric acid, because it said it completely reacted exactly, right? It exactly neutralized it, 1-to-1, complete neutralization. So you're going to do your molar mass here for your lithium hydroxide.
Really quick.
It's 23.95.
Can you go a little bit further?
0.948.
And that's going to get us into moles of our lithium hydroxide here. Okay. Now we want to use our balanced chemical equation to get from lithium hydroxide to your phosphoric acid. So everyone see that? And I can do that once it's balanced. So what's your coefficient for your lithium hydroxide? 3. So for every 3 moles of lithium hydroxide, what's the coefficient for your phosphoric acid? 1. 1 mole of phosphoric acid. Now, we need to put everything in the right units. So this should be moles of solute. Well, that's good. That's what this is going to give us, right? It's going to give us the moles of the phosphoric acid. But this bottom part, it should be liters of solution. What was I given in my problem? Milliliters. So we do have to change that really quick. Will someone do this calculation with the stop one?
What are you looking? Oh, 0.139.
Okay. The board kind of cut that off right there, but it should be 0.0357 liters. 71 liters. It was 9 for what?
0.139.
139.
Wouldn't you need to do molar mass again, very end?
No, because your molarity is your moles of your solute. Not your grams, your moles. But we wanted to stop with moles. If it had asked, now, this problem could have asked how many grams of phosphoric acid is in that concentration, then you would do that extra step if it wanted to know the mass. But since it's just wanting to know the concentration, we would stop with moles. And then you're going to take this number, divide it by this number, and what are we getting for a concentration? 3.89? Molarity. Okay? I don't, he's not here, I'm going to do this one. This is a dilution problem. You know it's a dilution problem because you have more than one volume and more than one molarity. As soon as you see one volume here, one molarity here, another molarity here, and it's asking for this second volume. It's your I think that's the one he loves to use. I don't know why there's letters in there. I just use M1, V1, M2, V2. Okay. So this is the molarity and the volume you're starting with. You do not have to change the units of volume as long as he didn't specifically ask for something. So you'll see here he didn't specifically ask for what's the liters volume that's remaining. So it's okay to use milliliters because the volume you're going to end up with will be milliliters. If we just plug everything in, ooh, that's good. This is a tricky one. Someone catch me. I intentionally just made a mistake. Tell me why. Why did the concentration go higher?
You put your first, you need to swap.
Yes. This should be swapped. So what he was really asking for was the original V1. It would still work, but you're going to have the wrong unit on it. So be careful on that. Whatever is your more concentrate is what you were starting with. What he's really asking here is how you made that less concentrated solution. So he's saying, what volume did you use here to make that less concentrated solution? In your dilution problems, your M2 should always be lower. You're diluting it so your concentration should go down because you've added more solvent. So your higher molarity is what you're starting with, your concentrate. Does somebody want to do that one really quick?
I got 31.
31.25?
It would just be 31 visual matrix.
Yes, that'd be 31 milliliters.
Oh, really quick, the difference between the polyprotic acids and ionization.
They're the same thing.
Okay.
So polyprotic acids, all polyprotic means is it's going to have multiple levels of ionization.
Okay.
And it will have as many ionizations for as many acidic hydrogens it has. Most of your acids only have one ionization. It's only got one acidic hydrogen. Weak acid, two-way arrow. Now, this still has acidic hydrogen, so it can still lose more. Really quick, one definition. What is that?
Amphoteric.
Amphoteric because
It can lose or gain the hydrogen.
right. It can go through another ionization here and lose one more hydrogen.
So it's just acids that can lose more hydrogen.
They have to have an acidic hydrogen still so that they can lose another,
And
but
does that have to be negative?
they have to have a negative charge so that they can attract a hydrogen to
So
them.
negative.
So this guy here and this guy here are both amphoteric. This third ionization wouldn't be because he doesn't have any acidic hydrogens left. He's just negative. Okay? Last question. Anything?
Can we take our test?
What if we blindfolded everyone and then you passed your test to the right, even though we answered them out loud? How would that go? I think the answer is 12. 24. Take the test blindfolded of your neighbor. No, someone would peek.
Here we go again.
Or can we take one more?
I have to count it, otherwise I'll be like, giving you